Our next speaker is Nicholas Rhinehart. He'll tell us about deep imitative models for flexible inference, planning, and control.
Okay, hi everyone. My name is Nick Rhinehart. I'm a PhD candidate at Carnegie Mellon University. I'm going to talk to you about some joint work with Rowan McAllister and Sergey Levine on deep imitative models for flexible inference, planning, and control. And so hopefully by the end of this talk, you'll have a better idea of some of the tasks we're solving here. It's an autonomous driving scenario. And basically the high-level algorithmic idea is we're going to use high-capacity imitation learning for model-based planning. Okay, so our motivating application is autonomous driving. There are a few key goals that we want to solve in this application. We want to follow the rules of the road. Okay, so that's very obvious. We want to be able to adapt to new tasks. So in addition to following the rules of the road, we're generally going to put the vehicle in new situations, and then adapting means generating a new behavior for that new task. So essentially, we'll have a data set of demonstrations, but they won't necessarily cover all of the behaviors we want to generate. And finally, we want to do this without any trial and error learning, because in this scenario, trial and error learning corresponds to crashing the vehicle in order to learn. So we want to avoid that. Okay, so a couple common approaches you might take towards these goals are model-based reinforcement learning and some standard imitation learning approaches. And they have a few pros and cons. So with model-based reinforcement learning, it's pretty nice because once you're given a reward function, you can adapt to new tasks if the reward function is well specified. You can use this reward function in your learn model to plan, and these plans are generally pretty interpretable, which gives you a good idea of what's going on in the system and what's going to happen as if you try to execute this plan. And finally, it has this sort of significant downside of you have to put a lot of energy into specifying the reward function well. And so often you'll have to do a lot of handcrafted engineering, and any misspecifications that happen result in behavior that you don't expect. So imitation learning gets around this problem by, instead of requiring a really well-crafted reward function, you can just use observations of expert behavior to learn a model. So you don't need a reward function, you just need someone to demonstrate how to perform tasks. But this has a few downsides of imitation learning generally isn't very interpretable. So if you're learning policies with imitation learning, they just output controls. And so given a new situation, the policy is just going to be spitting out these controls, and you don't really know the high-level plan it's trying to execute. And an additional downside is imitation learning is generally used to in the same settings that it was trained for. So it's pretty difficult to adapt it to new tasks, although there are a few approaches that you can take. Okay, and so our approach, called deep imitative models, is trying to get the best of both worlds of model-based reinforcement learning, so we're learning a model, and imitation learning, we're learning from demonstrations. So how do we do this? In this scenario, we have some input, so these large feature vectors, incorporating past positions of the vehicle, and LiDAR. So we have some 3D scan of the world, and we're doing this in simulation. So in the top middle, you have a LiDAR scan, and on the right, you have this frontal view showing you the scene. Okay, so the learning step for an imitative model is, given demonstrations from an expert, we want to learn a trajectory distribution. So this is a probability density function over trajectories, which are a sequence of states, fixed length, given this side information phi. So essentially, this distribution is going to be predicting what the expert will do in new scenarios. So given a new scenario, you can sample from it and evaluate the quality of any given trajectory. And that second property of being able to evaluate is what allows us to plan with the model. So at test time, we are given some abstract goals, for now abstract, and we are going to plan a trajectory as an inference procedure using our learned model over expert trajectories, and incorporating some task constraints. So skipping the derivation a little bit, you end up with these two terms. You have this imitation prior term, which measures the quality of a candidate trajectory, basically how expert-like is a candidate trajectory. And then you have this goal likelihood term. So given your expert trajectory, what is the likelihood that you achieve some abstract goal? Why are the goals abstract? Okay, let's make them concrete. So imagine you want to plan the model to just a final position. This is kind of the simplest goal task you might imagine. You can do this with a goal likelihood that's just a normal distribution centered around the last state in your plan. And so accompanied with a goal position that you want the model to navigate to, you essentially will end up with plans that don't arrive at the goal state are highly penalized under this. You can do fancier things like plan to a sequence of positions. So because we have this distribution over trajectories, these objects as trajectories, as opposed to imitation learning, you don't have trajectories generally, we can plan to a sequence of provided goals, basically matching positions where we want the car to go to. We can also plan to goals optionally. So given a bunch of different positions, the model can decide which goal it likes the most, which is the most expert-like goal. And then finally, we can also incorporate some costs to sort of modify the behavior. So these costs don't need to fully specify what it means to achieve the task. We can just use them to modify the behavior in various ways, such as imagine we have potholes in a new environment, and we never had any demonstrations of what it means to sort of drive around potholes. Well, if we have some cost map that corresponds to these potholes, we can plan and incorporate basically our trajectory distribution for the expert in addition to this cost. And so we'll end up with trajectories that are as expert-like as possible while sort of meeting this adapted goal task. Okay, so I'm going to kind of gloss over how we're learning this model, but you can find more details in a paper earlier this year called R2P2 at ECCV 2018. So we're learning, but I'll talk to you about a few of the key highlights from it. We're learning an analytic density function. So this is really important for the planning because it allows you to evaluate the expertness of a trajectory. So if you try to use a GAN or a VAE here, it's not really applicable. We need an analytic density function. And the way we're doing that is with an invertible generative model. So the objective function we use during learning is just this symmetric cross entropy. So we are penalizing mode loss or false negatives, and we're penalizing false positives basically through some cost map style structure. Okay, so once this is learned, we get a distribution that is multimodal. So you can see on the right many different predictions for what could happen. And it's also precise. The predictions aren't all over the place. They're sort of all generally plausible behaviors. So these are two important attributes to have in your deep imitative model. Okay, so the most standard way, or basically our most basic task that we can use this model for is once you've done the training, so this blue box, you can construct an imitative planner. So it's basically a planner that's incorporating this learned model over expert trajectories and use it to navigate to faraway goals. And the information that we have for the faraway goals is the sequence of waypoints, as in the bottom left. So there's these positions that are separated, for instance, by like 20 meters or 30 meters apart, and we are doing receding horizon control where at every few steps we give it a new waypoint. We plan using the imitative model, so that's sort of the crux of where the learning is being applied. And then we get out these set of trajectories that are scored by their quality under that objective criterion. And note we are doing all the modeling in state space. So all we do is, and the way that we get around, or the way that we avoid modeling actions until the very end is just by using a PID controller on top of our planned trajectories. Okay, so this is, I guess I'm running out of time a little bit. Our most basic experiment is this navigated driving. We test a few hypotheses with respect to model-based reinforcement learning and some conditional imitation learning approaches. But let me get to the more interesting experiments where we're really generalizing to new behaviors. So again, it's this pothole scenario. We've never observed what it means to avoid a pothole. And we still want to do this same navigated driving task. So we're still trying to navigate to faraway goals. So we can see that by incorporating this pothole cost, we can miss most of the potholes while still sort of achieving our other objective of navigating to the faraway goals. Another experiment is, what if we had noisy waypoints? So what if our localization is bad, or there's some bias or variance in our waypoints? So this is requiring the model to kind of tease apart what is a good or expert-like place for us to plan to. And so the first experimental setting is if I have half of my waypoints are good and the other half are high variance, can the model sort of pick under its planning, basically choose among these options which is the sort of like the cleanest one to plan to? And so we see the model doesn't get too much worse by planning with these high variance goals. And then the final task is, what if we have high bias in our goal positions? And we test this with just putting all of our waypoints on the wrong hand side of the road. And we're saying plan to these waypoints. So what happens is our plans end up staying on the correct side of the road, so it's internalized the expert behavior of staying on the correct hand side of the road, but it's still sort of in the plans are still sort of in the general direction of the provided waypoints. Okay, so to conclude, this is a framework for model-based imitation learning, and if you have some questions, just check out our paper, and that's all I have.
Thank you. We have time for a few quick questions.
Thank you for your talk. So my question is, can the test distribution be different from the training distribution of trajectories? I mean, even if the test trajectory or test task might be like sampled from out of the training distribution, can it work as well?
Right. Yeah, so that does happen in this case of trying to avoid potholes. You're pushing the vehicle into this other lane, and it's never seen demonstrations there. But part of the objective is trying to explicitly optimize for trajectories that stay in the estimated distribution of behavior. So you do kind of get this correction effect of where it's trying to go back to where where the data distribution is. Yeah.
Thank you very much.
Hey, thank you. So I guess I was just wondering, it sounded like you weren't replanning on every frame or control step. So is there any option for feedback from like the lower part of the control to say maybe you're starting to go off into a non-expert area, basically?
Yeah, so you could use feedback like measuring essentially, well, you could replan first of all and say whether or not your new plan is very different from your old plan, and if it's not, then you're probably fine with your old plan. There is feedback in the PID controller, right? So it's recorrecting based on, or it's sort of tracking the trajectory as you plan, but there's no mechanism for detecting if you're sort of out of distribution without the planning.
Okay, thank you.
Mm-hmm.
All right, let's thank the speaker again.